All right, good afternoon everybody. My name is Richard Lander. I'm a senior cloud native architect at VMware. I've worked at VMware since late last year when VMware acquired Heptio, where I was on the field engineering team. And before that I worked at CoreOS on the field engineering team there as well. So I've been helping enterprises adopt Kubernetes and cloud native for a few years now. And one of the things that I've found really helpful in that endeavor is to help engineers understand what makes Kubernetes so effective in what it does. And so that's what we're going to talk about here today. Before we get started, I just want to get a feel for some of the tools that you may or may not be familiar with, because I'm going to reference some tooling here today, and I just want to make sure we're on the same page. So has everyone used the kubectl or kubectl command line tool? A few? Okay, great. And Prometheus monitoring software. Has anyone used Prometheus? Is familiar with it? A few. Okay, great. That's helpful. And for everyone else, does everyone at least know what a pod is? A pod in Kubernetes? Okay, cool. Good enough. So, as I'm sure everyone's aware, Kubernetes popularity has exploded over the last few years. And there's a good reason for that, is because it can businesses can derive a lot of value in improved efficiency and effectiveness in delivering software. So that then leaves us in the position where we need to understand this complex software system in order to optimally utilize it, which is really important if you're going to derive that business value, right? So as we're going through this, I'd like you to not only think about how Kubernetes works so that you can utilize it better, but also take the engineering principles from Kubernetes and think about how you can apply it to other distributed software systems, because Kubernetes is an excellent example, one of the best out there, of a distributed software system. So there's lessons that we can learn from it when we're developing software that our business uses to make money. So legal disclaimer. And these are the 4 core concepts that we're going to talk about here today. The first is the API-driven nature of Kubernetes, why that's important and how you can leverage it. The other is the control loops, which form the core of the autonomous behavior in the system. Then we're going to talk about extensibility in Kubernetes and how you might want to extend, how and why you might want to extend the Kubernetes API. And we're also going to talk about the community that built this project. So the first core concept, the API-driven nature of Kubernetes, is perhaps the obvious of the 4. But a quick note on that subject, with few exceptions, almost all modern software should be API-driven. Now that doesn't necessarily mean you need to expose an API on every piece of software that you develop, but that's one of the reasons why Kubernetes is so useful, in that you can leverage it to make your software API-driven. So with Kubernetes, the API is the interface, which is to say other software that wants to utilize Kubernetes is a first-class citizen in that ecosystem. And that's really important. To leverage the maximum usefulness of Kubernetes, it needs other software to use it, all right? Even when a human user uses Kubernetes, they do so through the API. They just don't do so via a tool like kubectl or kubectl, which is a command line tool. And when you issue the command kubectl create pod, all it does is turn that command into an API request and sends it to the API. And when you use the Kubernetes dashboard, which is a graphical user interface that you can use to create and delete resources, that translates your point and click operations into API calls to the Kubernetes API as well. So, like I said, the API is the interface. So while Kubernetes certainly didn't invent the idea of API-driven software, it delivered a really superb rendition of an API to use, so that when you're developing software against it, it uses a lot of intuitive, natural conventions that make a lot of sense. Common patterns that are easy to use and make it very easy to understand. It's RESTful, of course, and it uses versioned API groups. For anyone that has developed software that uses some other API, and that API has made a change which in turn breaks your software, you'll greatly appreciate the value of versioned APIs to maintain backward compatibility, make sure everything keeps working in an ecosystem of integrated software. All the resources in Kubernetes use a common set of metadata, so it's intuitive to understand what you're dealing with as you're developing applications. And it's also, now I can say, well documented. The online documentation for Kubernetes has come along leaps and bounds over the last few years. And I'd also like to point out that individual Kubernetes APIs are also self-documenting in the sense that you can get the API versions and the resources that are available in the particular API that you're dealing with at any given time, which is important if you're dealing with multiple clusters which may be different versions of Kubernetes. So while the API-driven nature of Kubernetes may be the obvious core concept, the control loops are the important one. Because there's a future where autonomous software systems do almost everything for us. We'll deliver these high-level directives to them, and they'll go through a set of data gathering and problem solving to bring about these high-level desired outcomes. And they're going to do that all through this concept of control loops, and they'll do it much more reliably than we as administrators or human operators can ever do. So the first thing that I want to point out is that when you create a resource in Kubernetes, you issue a command kubectl create pod, you're simply making a record of intent. After that record of intent has been stored in the system, separate to that, there are controllers, various controllers that go to work to bring about that desired state. Okay? In the case of a pod, if you create a pod, there are several controllers that are interested in that resource. Okay? And they use what's known as level-triggered logic to bring that about. So level-triggered logic, or software that uses level-triggered logic, forms an accurate picture of what the existing state of the system is. It forms an accurate picture of the desired state, and it works on a continuous loop to reconcile that and bring about that desired state. Okay? And that is an important point to that is that it continually loops, in that if there is a condition that prevents it from bringing about that desired state that you've defined, it doesn't give up or crash. It continues to loop and attempt to bring about that desired state, so that if that missing condition is remedied, it can then bring about that desired state that you've defined. Now that's different to edge-triggered logic, which is event-driven. So think of calling a function and providing some input to that function, and it takes some action or returns some data back after processing it. It has no notion, generally speaking, of desired state. All it does is take the input, crunch it, and deliver output. If there's some missing condition in the processing of that data, it fails. It might crash. Preferably, it'll fail gracefully and log that output so that you can at least troubleshoot the situation. But it has no concept of desired state, which is really, really important to that level-triggered notion. So to illustrate that a bit further, I'm going to compare it to a little bit of human behavior. Because we as humans use level-triggered logic a lot. We look around our environment and form a picture of the existing state. Our imagination forms a picture of the desired state that we want to bring about, and then we work on a loop to bring that about. In a real granular, practical sense, when you're driving your car down the highway, you have several control loops that run. You'll check the position of your car in its lane. And if the existing state you find is that your car's drifted to one side or the other of the lane in the highway, you'll correct that and bring it back to the desired state, which is your car running in the middle of the lane. You'll also check the speed on a control loop. If you find that your speed is drifted too high or too low, you'll correct that and reconcile that with desired state, which is whatever speed you want to drive at, right? So level-triggered logic is really, really useful when you want to manage state. Now, that's not to say that edge-triggered logic is invalid or not useful at all. So going back to our driving a car example, if a car shoots out of a side street into the path of your vehicle, you better have some edge-triggered function that causes you to brake quickly or swerve in response to that. But the point is that edge-triggered logic is very stimulus response. It has a place, but if you want to manage state, level-triggered logic is what you want to do, or what you want to use, I should say. So now we need to talk about how that was implemented in Kubernetes. And the first thing is to design a resource. Now, a resource is a pod or a namespace or a deployment, whatever it might be. But it allows you to define the attributes that allow you to designate the desired outcome that you might want to bring about. So for an example, a pod, some of the attributes are the image, the container image that you want to run for your workload, and maybe a resource allocation of how much CPU and memory you want to give to this application that runs in your cluster. So once that resource is defined, then you can build a controller that uses level-triggered logic in order to reason about those attributes and it knows and teach it how to bring about the desired state that you have defined in your resource. So let's look at a practical example of what that might look like. So in the middle here we have the Kubernetes API server, and I've got etcd indicated here just to indicate that this state is actually stored in etcd. I've got the resource in the API server here, and as far as all the controllers are concerned, that's where it's exposed. So I've just put it in the API server, even though it doesn't actually exist there. So when you create this pod resource, there are different controllers that place a watch on that resource. And think of a watch as a notification mechanism, which is to say it opens a connection with the API server, and when the API server receives a new pod and stores that, every controller that's interested in a pod gets notified when a pod resource is created, updated, or deleted, okay? So a pod is created. So therefore the scheduler will get notified of this, right? And the scheduler's job is to assign that pod to a worker node in the cluster. So you remember in a pod we defined the resource allocation, how much CPU and memory we want to give to that pod. Well, the scheduler is interested in that because it needs to find a worker node that has that compute and memory available, okay? So the scheduler gets notified of this, and then it examines that attribute, like the resource allocation, and it goes about through a pretty sophisticated set of rules and functions to determine where that pod should live, okay? So let's say, for example, there are no worker nodes that have enough memory or compute for this pod to live. Well, it's going to continually check back and attempt to schedule that pod routinely on some interval. It just never gives up is the point. And the assumption is that some other system or application or human operator is going to remedy that condition and add a worker node into the cluster. And as soon as the scheduler recognizes that, on its next loop through, it'll find that it can schedule that pod, and when it schedules the pod, and this is really important to understand, the only thing that it does is update that pod resource in the API server, and it creates a new attribute which is node name, which assigns that pod to that node. And then the scheduler's job is done. It gives up. It knows nothing about any other process in the entire control plane because its job is done at that point. So the next controller that's interested in a pod is the kubelet. And the kubelet is the Kubernetes agent that lives on every node throughout the cluster. And its job is to run the workloads for its particular worker node, or a master node for that matter. So when the kubelet, which has a watch on all pod resources as well, when it gets notified that a pod has been assigned to the node for which it is responsible, that kubelet is going to take the attributes out of the pod like resource allocation and image name, and it's going to pass the image name over to Docker, or whatever container runtime you're using. And then Docker will actually run that workload, that container on the worker node. And so then once that is done and the container's up and running, the kubelet just updates the pod status to running status so that every other controller in the system now knows that this pod is running. So that's an example of defining a resource and then designing controllers to reason about that resource and bring about the desired state that you want, right? And the next thing I want to point out that's really important to do is keep that scope as functionally useful but as tight as possible, and then add additional functionality on top of that with other resources and controllers. So the way it was done in Kubernetes is that when you need to run some number of identical workloads for availability and capacity reasons, that functionality isn't represented in a pod or built into the existing controllers. A new resource called a replica set was designed, and a corresponding replica set controller. So a replica set manifest looks very similar to a pod manifest, but it has an additional attribute which is replicas. In this case we want 5 pods to run, so a replica set has replicas 5. And then the replica set controller, all it does when it sees that new replica set, it creates 5 pod resources. Now you could go and achieve the same outcome by creating 5 separate pod resources with the same resource allocation and image, but the replica set does it for you, and that's what it's for. And furthermore, it'll maintain that state. If you manually come in and delete one of these pods, the replica set will notice that because it'll have a watch. I haven't shown it there, but it'll have a watch on the pods as well, and it'll create a new pod to replace the one that you deleted. So it maintains the desired state as well as bringing about in the first place. Okay, so a replica set is created, the replica set controller notices that, creates all these pods. So the next resource that adds functionality on top of that is a deployment resource. And this is actually the most common way that people will deploy workloads into a Kubernetes cluster, is using a deployment resource. So the deployment manifest, again, looks very similar to a replica set in a pod. And when it's created, the deployment controller, which has a watch on that particular resource, will create a replica set. And when you first create the workload, it actually doesn't add much value at all. It's created a replica set and the rest of the chain of events carry through, right? When a deployment becomes really handy is when you want to update this workload. Let's say you have version 1 running out in your cluster and you've done some development, it's running in production, whatever the case is, and then you've done some development, created a version 2 of your application, you've built the image, you've pushed that image to your image registry, and it's ready to roll out into production. So this is when a deployment becomes really handy, because you can come in and edit that deployment in place and just change the tag on the image to v2, okay? When it's changed, the deployment controller notices this. It's notified of this because of this watch mechanism. And what it does in response is, by default, it performs a rolling update. And the way it does this is it creates a new replica set. And that new replica set will have the v2 image tag in it, okay? And it creates it with replica 1, okay? So now the replica set controller is going to respond, and you're going to end up with 5 of version 1 and 1 of version 2. And the deployment controller will also watch the pods. When that version 2, when that 1 is up, it will then change this replica set from 5 to 4, so that version 1 is now down to 4 replicas. Once that's done, it'll change the v2 replica set to 2 replicas. And when that's up, change v1 down to 3, and so on and so forth. It'll incrementally roll out version 2, and at the same time incrementally roll back version 1. And that's the default behavior of a deployment. So when it comes time to update your deployment, update your workload, that's where a deployment really comes in handy. So this is why I say Kubernetes is a fantastic example of a distributed application. These controllers know nothing of each other, and their scope is relatively tight. Sometimes it's a little complex, but that means that each of these individual applications can be developed individually and maintained with a much greater level of simplicity, and the blast radius of any change is much, much lower. All right? So that is how it's designed in Kubernetes, in the native Kubernetes system. So if the API-driven nature of Kubernetes is the obvious core component, and the control loops are the important component, this is the exciting one, because this is where we get to develop that future of autonomous software systems that I talked about. So just a word on why you might. So what this boils down to is you're going to create your own custom resources. Whereas Kubernetes has pods and replica sets and deployments, you're going to design your own custom resource. And then you're going to design develop your own controller to reason about those resources. But that brings to mind, well, why would you want to do that? What's a useful use case for developing your own Kubernetes controller? And there are thousands of use cases out there. For example, you may have your own corporate DNS system, and when certain services of type load balancer are created, you might want to manage DNS records or something of the sort, and you might want to do that in a level triggered way. But I think, and there are tons of other examples like that, like managing your infrastructure inventory in response to scaling of Kubernetes clusters, for example. But the really compelling use case, I think, is developing operators for your company's software. So when you hear the term Kubernetes operator, there's a really misunderstood term, but it is simply a class of Kubernetes controller, and it usually manages some complex stateful application. Some examples out there are the Prometheus operator, the etcd operator, but they're just Kubernetes controllers. They have custom resources and custom control loops that manage these resources, right? So if your company has some e-commerce web application that consists of deployments and stateful sets and services and config maps and secrets, you can develop your own controller to manage and maintain the state and make sure that it's a level triggered condition whereby that state is maintained and it's constantly checking for a variation from the desired state and bringing it back and reconciling that constantly. So The process is the same. You design that custom resource with the attributes that allow you to define the desired outcomes, and then develop a controller that can reason about that and continually loop and bring that desired state about. And again, keep the scope for every particular resource as narrow as you can, and then build upon it with other resources and control loops. And okay, I'll give you a quick example. So Prometheus, I mentioned earlier, is monitoring software, and it's very commonly used in Kubernetes. The important thing to know about Prometheus is it runs on a scrape model. It goes out and scrapes metrics from the applications that you run. Some monitoring systems just expose an endpoint and then applications send metrics to the system. Prometheus does it the opposite way around. It goes and scrapes those metrics, right? And the Prometheus operator is a piece of software you run in your cluster that will manage those Prometheus servers for you. So when you deploy a Prometheus server, you have to configure it with all of the applications that you have running, like what its address is, the port and path that it's exposing metrics, and it'll go and scrape all those. But for anyone that is managed Prometheus, it is not trivial. There's a lot of human toil goes into deploying and managing and configuring Prometheus. But if you run the Prometheus operator, and it has its own overhead of complexity, but once you get around that, you deploy the Prometheus operator into your cluster, and then you create a custom resource called a Prometheus. Kubectl will create a Prometheus in the API. The Prometheus operator sees that because it has a watch on that resource, and it knows exactly how to handle that. And it'll create a stateful set, which is basically a stateful deployment. It'll deploy all this and a config map into your cluster, and before you know it, you have a Prometheus server, and it's so much easier. The reduction in human toil, just there alone, is magnificent. So now you have a Prometheus server. It's ready to scrape metrics, and you have your application, and it exposes Prometheus metrics. But at this point, Prometheus knows nothing about your application. Okay? It's just there running, and it's ready to scrape metrics, but it's not doing anything yet. So then you create another custom resource that the Prometheus operator watches for, and that's called a service monitor. And some of the attributes that you'll define in a service monitor are the address for your application, the port and the path at which you expose that, and you use labels and selectors to identify it with a particular Prometheus server. So you create that resource, the Prometheus operator notices that, and it goes, I know what to do with that, and it goes and adds a scrape configuration to your Prometheus server, and bam, you've got Prometheus now scraping metrics from your application, and monitoring, at least for day one, is solved, right? So that's an example of how an operator, which is just a Kubernetes controller that manages a complex stateful application, that's in concept how it works. Now, Prometheus has two other custom resources and controllers that it uses for things like Alert Manager, but we won't go into that today. That is for another day. So, the community is the fourth core concept. And while these engineering principles that we've talked about that make Kubernetes so effective and successful drew in people in the community and engineers to work on it because they saw the value in that, it's still the community that implemented those features. And without the community, there would be no Kubernetes. And that's really, really important to recognize. So Kubernetes is a complex system. There's no getting around that. But when you have as many contributors as the Kubernetes project has, that complexity becomes much more manageable. As engineers and system admins, it's often really tempting for us to avoid learning the complexity of a system like Kubernetes because at first it doesn't feel productive. You're just in a lab toying with something, you're not doing anything, you're not piecing anything together in production. It sometimes feels much more productive to start putting your own system together and developing this and configuring all of these things because on day one you have stuff working and you're putting it all together. But that very quickly meets diminishing returns when compared with, in the long term, learning a complex system like Kubernetes that is supported by such a huge community. Bugs are fixed, use cases are fleshed out, and a ton of people are using it and developing it and building those features in that you can then benefit from. And especially if you then give back and contribute to that community, it becomes a very rewarding and, in the long term, much more productive outcome. So, what is the whole point? What are we doing all of this for? We're just reducing human toil. And it's very important that you orient yourself to that objective on a routine basis. Okay, so just as computer file systems remove the human toil of having to create paper documents and file them in physical filing cabinets, and just like e-commerce removed the human toil of having to travel to a physical marketplace in order to trade goods and services, Kubernetes is removing a tremendous amount of human toil from deploying and managing software systems. And as software takes over the world, that impact is going to become more and more and more significant. And because the time that you save in having to toil over deployments and managing deployments is time that you can invest in developing and improving the efficiency and effectiveness of other systems, right? And that improves conditions for everybody involved. So, the bottom 3 links here are great further reading material if you want to read about some of the stuff that we've talked about here today. And delve into those subjects a little more, like level-triggered logic and things like that. But that top link is the one I really want to point your attention towards, because Kube Builder, in Git, this is the GitHub project for a project called Kube Builder. And Kube Builder is a software development kit that provides a framework for you to define these custom resources and to build the level-triggered control loops that will manage those resources. So if you're a Go programmer, or if you know a Go programmer, or if you're interested in Go programming, absolutely check that project out, because that's exactly what will lead you towards being able to build these ever-improving autonomous software systems as we move into the future. And that's all the material I have. I hope you found it useful. Please fill out the survey. Your feedback is greatly appreciated. And that's all I have. Enjoy the rest of the conference. Thanks, everybody.